Hello, and welcome to this video where we're going to be talking about our new unit, and that unit is something called momentum. Now, that's a word that you've probably heard before, and you might have some ideas about it. And what we're going to try and do is take your general ideas about it and put it into scientific language, introduce some new vocabulary and some new relationships. So here we go. Momentum. What is it that you think about when you think about the word momentum? So stop the video for a second and brainstorm a little bit about ideas that you believe to be true about the concept of momentum. All right. So hopefully when you think about the word momentum, you think about the idea of things continuing moving, right? That things with momentum kind of like keep going, right? You might also think about objects, quote unquote, having momentum, right? So I have momentum. That's actually a good verb to use with the concept of momentum. Maybe you went into sports analogies, because there's some really good sports analogies to use when talking about the concept of momentum. When we say a team has momentum, what do we mean by that? Well, hopefully you start thinking about something along the lines of a team with momentum will keep winning, right? Or you think about during a game, a side that gains momentum goes from losing to winning, or they're on a specific pathway that's different than what they were doing. And there's a distinction then between having momentum and something gaining momentum, right? One is a present state, and the other is a change in that state, right? So that's the difference there. It's about a state versus a change in state. Okay. Now, believe it or not, this is a really good way of thinking about the physics concept of momentum. A team with momentum will keep winning, right? Essentially, this team is hard to stop, right? So a team with momentum, difficult to get them to lose. They're on a roll, so to speak. And that actually is going to play into our idea of momentum, because momentum is actually going to be defined as a relative measure of how hard it is to stop an object. Okay, relative measure of how hard it is to stop an object. That's going to be with the number that we're going to ascribe to the concept of momentum, what that number is going to tell us. The larger that number is, the harder it is to stop that object in general. Okay, now there's all sorts of details with it, but it's a good way of framing and thinking about this concept. So if we think about factors that affect then how hard it is to stop an object, well, when would an object be difficult to stop? And there's two main factors that affect how difficult an object is to stop. And the first of those is, of course, the mass of an object. I think we would all believe, actually, let's go momentum here, that when you have more massive objects, they are harder to stop, right? It is harder to stop a moving train than it is to stop a moving grandmother, whatever. What's the other factor that matters? Well, the other factor here is how fast the object's going. Now, I can put either speed or velocity into that. So what's going to determine whether I put speed or velocity into this blank here? Because I think first off, we'd understand that when a car is going 40 miles an hour, it's harder to stop than a car going 5 miles an hour. I mean, not that we'd like to stop ourselves a car going 5 miles an hour, but something stopping that. It's easier at 5 miles an hour, or it takes not as much effort or time to do it at 5 miles an hour than it would at 40. Now, what goes in this blank between speed and velocity is going to be dependent on whether or not we need momentum as a concept to be a vector. And so what we're going to say is a reminder from early in the years that, yes, we did decide that momentum was going to be a vector concept. Well, decide, I told you, but there it is. And we'll see why it's a vector through the course of this process, which means that if momentum is a vector, what we want to have here is velocity, because as we've argued before, vector quantities need to be built upon other vector quantities, right? Or at least our new ones. So what does that mean for us? Well, let's put this in equation format. So mass, m, velocity, v with a vector sign. When we do problems, we're not going to put that vector sign there, but once again, I'm just doing this for theoretical sake, so I want to do it really properly the first time. And momentum, what symbol? Well, obviously we're not going to use m, right? Because m is mass, already taken, right? Oftentimes then, we don't want to use like capital M either, because we just saw in that last unit that big masses we often use capital M for. So oftentimes in science, when you run out of English, you kind of go to other languages, like for example, Latin, right? So if you've ever seen lead, right? Not seen lead, of course you've seen lead, but lead in chemistry, what's the symbol on the periodic table for lead? Right? It's Pb. Why? Because the Greek letter, the Latin name for lead is plumbum, right? Pb. Same thing with things like iron, ferrous. So maybe they do that for momentum as well. So momentum in Latin is, of course, momentum. So not going to work, right? So we're stuck with our m's. So what do we end up going with? We end up going with actually the lowercase letter p. Why? Well, Newton is the one that defines the word momentum, and he has a reason for using that lowercase just regular letter p. If you're interested, we can talk about it at some other time, right? But it is a vector, and it is actually really important that it is a lowercase letter p, because in the next unit, we're going to have something that is uppercase letter p, and we don't want to get them confused. So we're going to box this, and there's our equation for momentum. P equals mv. So what are the units of momentum then? Well, if I do bracket P, that would be the units of mass times the unit of velocity. So that's going to be a kilogram times a meter per second. And by the way, there's no fancy other way to do it. It's just well, actually, there's one, but we'll deal with that later. But there's no thing like how we said in the past, like, oh, well, that comes up so often we name it something else. Nope. The units for momentum are a kilogram meter per second squared. Kilogram meter per second squared, kilogram meter per second squared. I'm going to leave a little space here because there is one neater way to write that. And maybe you can think about what that is without denominators, because we like that without denominators. But we'll come back to that. So from here, what I want you to think about is, well, let's think about situations in which an object has a lot of momentum and situations in which objects doesn't have a lot of momentum. So stop the video for a second, jot down something, a situation where something has a lot of momentum, and jot down something, a situation where it has a little bit of momentum. All right, so generally, the first time I ask that question, what most people say is like, airplanes have a lot of momentum, cars have a lot of momentum. And then I get to say, wrong, right? Why is it wrong to say cars have a lot of momentum? Well, look at the equation. Sure, a car is massive, but a parked car doesn't have any momentum. A school building has a lot of mass, but not going anywhere, so it doesn't have momentum. And that's why before in the prompt, I said, name a situation in which an object has a lot of momentum, because momentum is not an inherent property of something. It is a property or a description of something while it's moving, right? Which is why kind of having is a good verb to go with momentum, because it only has it in a certain set of situations, right? It's not defined by that. But what would be a situation like a car driving would have a lot of momentum, an airplane flying would have a lot of momentum, an asteroid going through space has a lot of momentum, right? Those are all massive objects that have a lot of momentum. But what's an object that's not that massive that has a lot of momentum? Well, hopefully you said a flying bullet. Remember, momentum is a relative measure of how hard it is to stop an object. I think we'd all agree a shot bullet is not something that we would like to stop, right? Because that's going to have a lot of momentum. Has a small mass, but it has a larger velocity, a very quick velocity. So you could have small objects that have large momenta and big objects that have large momenta. So what's an object that has small momenta? Well, maybe a tortoise walking, right? Not that massive, not that fast, right? A marble rolling across a table, not that massive, not that fast. So there you go. There's your concept of momentum. So momentum in and of itself is rather boring, right? Because that's the entirety of the momentum concept. But we don't really care about momentum per se. What we're going to care about instead is what happens when momentum changes, right? So let's talk about what must happen for momentum to change. Okay? Well, if we go back to that equation, P equals mv, if momentum is changing, either the mass is changing or the velocity is changing. So let's just talk about that for a second. The mass changing is a very weird thing, right? Objects don't generally change mass as they go along, right? Maybe if I'm running along, stuffing Oreos into my face as I'm running, my mass is changing. Very unfortunate situation. Maybe you leave your sunroof open on your car as you're driving in a rainstorm. The mass of the car is constantly increasing over time. A rocket ship actually goes because it's shooting hot gas out of its bottom end, right? That thing is losing mass over time. Those are very complicated scenarios. So even though mass can change in these situations, we're not going to have that in this class because we'll find out later on for the mass to change or to deal with problems where the mass is changing over time, you actually need calculus. Newton does explore that in the Principia. We won't. So we'll be dealing with constant masses. Not that you can't have a changing mass, but that's outside of the scope of our course for the reason I just talked about. So in other words, for momentum to change, therefore, there must be a change in the velocity of the object. All right. So any change in velocity means there's a change in momentum. Well, what does that mean? Well, if there's a change in velocity, therefore, the object must be accelerating, right? Because the rate at which the velocity changes is the acceleration. So anytime there is a change in velocity, there must be an existing acceleration. And if the object's accelerating, well, what's causing that? Well, we all know by Newton's second law, what causes accelerations is, therefore, a net external force must be acting on the object. Okay? So for there to be a change in momentum, delta P, there must exist a net external force. Okay? Now, in the past, we've just written net force, and I said net external force back when we were studying Newton's laws, but we kind of let that fall away. This is the unit where actually that concept of external is going to become really critical. Not this week, next week. So I'm going to bring that up right now and start talking about net external forces throughout this entire unit, right? So any change in momentum is linked with a net external force. There we go. So I want to define another new thing, and then we'll kind of connect all this. So I'm going to define a word that we're going to call impulse. Now, impulse is a really simple concept that people have a tremendous difficulty with, okay? Because it doesn't seem like we need the word. And we kind of don't, to tell you the truth, because when I define what it is, we can see there's an easy enough way to talk about it. An impulse is defined as the change in momentum of an object. That's it. Impulse is the change in momentum. So we define impulse. Impulse is delta P. Now, because momentum is a vector, that means impulse is a vector. Now, in most textbooks, they give you a symbol for impulse, and that symbol for impulse is capital letter J, vector. I am not going to do that. I'm never going to write that. Why? Because delta P means impulse, and delta P literally tells you what the concept is. So I don't want to give a word to obscure meaning. Impulse, change in momentum. So let's see what that means. Let's expand that out a little bit. Anytime I have a delta, delta always means final minus initial. Okay? So impulse, the final momentum minus the initial momentum. There we go. So what does that mean in practical terms? Well, let's say I have a mass. That mass is a 20 kilogram mass. And let's say it has an initial velocity. So there it goes, initial velocity of 10 meters per second. Now, since this is a vector problem, right away, the first thing we're going to do is we're going to make a declaration, because we always make declarations in vector problems. I'm going to say to the right is positive. Now, something happens to that object that's moving. So there's my mass that's moving. That finally, this thing has a 15 meter per second velocity. Okay. And so if I were to ask, well, what impulse was provided to the object? So let's talk about verbs here. That's often one phrasing. What impulse was provided to the object? We also can say what impulse was imparted upon the object. So was provided to, was imparted upon. Was imparted upon is actually Newton's language from the Principia, or at least a translation of that. Or what impulse acted on the object. And those are the three ways that we talk about the concept of impulse. Well, this is pretty simple and straightforward, because all we're going to do here is we're going to go, well, the final momentum here is mass times the final velocity. So 20 kilograms times 15 meters per second. And that is 300 kilogram meter per second. And the initial momentum was mass times initial velocity. Now, technically, this is final mass times final velocity, initial mass times initial velocity, but we talked about that as mass as being constant. So 20 kilograms times 10 meters per second is equal to 200 kilogram meter per second. Now, let's talk about the vector nature of this, because I said to the right is positive. So this is technically 8 plus 15, and that's plus 300, and that is to the right. And this is plus 10, and this is plus 200, and that is also to the right, okay? That means then, what is my impulse? Well, my impulse here is equal to P final minus P initial, or a positive 300 kilogram meter per second, minus a positive 200 kilogram meter per second, and that gives me a positive 100 kilogram meter per second, where that positive here means right. So the impulse here was 100 kilogram meter per second to the right. Yep. It describes literally how much the momentum of this object changed. So in other words, this object has become harder to stop by 100, right? Or if we're looking compared to the beginning, this thing has become 50% harder to stop. That's the way we talk about this, okay? So why it is important that momentum is a vector? Well, let's look at the same situation, but now let's have my initial velocity being 10 meters per second east, and my final velocity is equal to 15 meters per second west. And we will maintain our positive is to the right declaration, and our mass is still 20 kilograms. So it's a little off there, right? So hopefully you can see that the only difference here in this problem here is that the final momentum, mass times VF, would be 20 kilograms now times, if we're going to use our declaration, negative 15 meters per second, or it is going to be negative 300 kilogram meter per second, and the initial momentum is still that positive 200 kilogram meter per second. Oops. I'm just going to steal that from before. So what does that mean about our impulse? Well, our impulse then is going to be P final minus P initial, and it's negative 300 kilogram meter per second minus a positive 200 kilogram meter per second, or negative 500 kilogram meter per second. So if you think about that now, the impulse imparted upon this object was greater than it was before. Well, why? Well, here, all I'm doing is I'm bringing this thing from going to the right to going to the right faster. Yeah, it's not a big change, right? Not a big change. But this one, I'm going from the right to the left, or east to west, however we want to frame this. So what has to happen for that to occur? Well, a force is going to have to act on this, and that force is first going to have to slow down that object from going 10 meters per second east to rest, and then speed it up from 0 meters per second to 15 meters per second west. That is a much larger change in the physical reality of that object, and that is denoted in the momentum change of this object, that its speed didn't change by, well, its speed changes by the same amount here as in the other problem, but because of the vector nature of momentum, the impulse is vastly different. And that is why it's important, because now we're getting to the next layer of this is, well, what's causing, whoops, I thought I turned my phone off. I said before that impulse is caused by force. So if we think about it, what must be the direction of the force that's causing, well, let's go back to this one, this change. Well, we know for an object to speed up, the acceleration has got to be in the same direction as the velocity. And we also know that net forces always act in the direction of the acceleration. So there we go. The net force here is to the right. Interestingly, down here, the impulse is to the right. Wonder if that's going to be a thing. The answer is yes. Over here, this thing is going to slow down while moving to the right and then speed up left. Therefore, this thing must be accelerating to the left. Therefore, the net force here is to the left. So what we discover here, and notice our impulse is left, is that the impulse imparted is always, and this is going to mean always, in the same direction as the net force. All right, getting there. So now we need to I want to make an equation between impulse and net force. So let's think about this. Well, the larger the net force acts on an object, what do you think is true about the amount of change that occurs? Well, hopefully what you said there is greater net force means larger change. And that's going to be true. The impulse on an object is going to be directly proportional to the net external force that acts upon it. Now, I'm also going to put the vector signs above it because this also says that in my equation, I want the direction of this and the direction of this to be identical to one another. So that's going to be an important thing about this equation. So now let's go back here and talk about, well, I want to change from 10 to 15 meters per second. If I know what the force is, do I know how much the momentum changes by? Well, no, because if you think about this, if I act with a 10 Newton force on this mass, I will know what its acceleration is. But that won't tell me what its impulse is, because if I leave that force acting on that object and just leave it on, leave it on, leave it on, leave it on, that thing's going to not just stop it, like speed up to 15 meters per second. It's going to keep on speeding up and speeding up and speeding up and speeding up. Therefore, the amount of change that an object undergoes is not only related to the amount of force that's causing that change, but also the amount of time that that force acts. The longer the time the force acts, the greater the change is going to be. Hopefully that makes sense, right? Therefore, I can say that the impulse is directly proportional to the length of time over which the force acts. Now, normally we just say t. I'm saying delta t here, very specific, because I want to say delta t, we're going to define that to be as the length of time over which the force acts. Oftentimes this is going to be the time of what I'm just going to call the event, whatever that means, the event, okay? So if I put those two notions together, what I end up with is an equation that says delta P vector is equal to F net external vector delta T. okay? We're going to box that. Notice here, delta t has to be positive, meaning that these two vectors will always point in the same direction as we argued. The bigger the net force that acts on something, the greater the rate of change, the longer the time, the more amount of change that can occur. And this is recording the amount of change that can occur. Okay, so if I look at this, I can see another thing. Well, actually, let's look at what's going on here. The left side of this equation, P final minus P initial vector, that describes the amount of change. The right side of this equation describes the reason for the change. And so that's the nice thing about this concept is I can find impulse by looking at something before an event and after an event and calculating it, or I can figure out what's going on by looking at what's causing the change, what the event actually is. And we're going to find out that there's events that are so complicated that it is easier to observe what happens before the event and after the event. And by knowing what's true before the event and after the event, I can figure out some things that happen during that event. And we'll talk about an example of that later. The last thing in this section is going to be units. If I look at this, the units of delta P, well, looking at this equation, that looks like a Newton, right, because F net external, times a second, or a Newton second. Now here's the thing. Delta P is going to have the same units as P does, right? Because delta P is just P final minus P initial. That must mean a Newton second, going back to the very first thing that we talked about, or was that the first page? Yes, it was. That P has also units of Newton second, just Newton second, Newton second. A lot of people want to say newtons per second. Wrong, wrong, wrong. Newton second, just right through. Newton second, okay? So these two must be equivalent, and they are, because hopefully you remember a Newton is a kilogram meter per second squared times a second. Boom, boom. There you have it. The Newton second is equal to a kilogram meter per second. And tell you the truth, I tend to write Newton second as the unit of momentum no matter what I'm doing. I find it more convenient, and I hate denominators. And it's less to write, so there we go. So there's our overview to momentum and impulse, and this equation here that connects them, which is something that's called and I just want to name it, the impulse momentum theorem. Okay, impulse momentum theorem. So I'm going to stop this screencastify, take yourself a little 5-minute break, then come back and look at the second part. I have some videos and some applications to look at based on this.